Oh, whoa, 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 yo, no way. Yeah. Here we go. You know it's starting. It's happening. You know it's gonna be going. It's doing its thing. Okay. What? What the heck? Like, okay. Sorry, everybody. I had a phone. My camera just literally shut off on me. Um, let me get back on in a second. Yeah, sorry about that. It shut off right as I hit the stream button. But we are here. We're going on. We're gonna get the show going, anyways, even as this thing comes on. So I want to thank everybody for showing up to 3D Changes Perspective, so I can change your perspective today. You probably saw the title. It's gonna be a lot to do with entropy and entropy and antropy. Very fun topics. But before we get into that, let's go ahead and thank today's sponsor, randomness.com, for sponsoring not only us but the Bitcoin Live network itself. You can go ahead and jump on randomness.com to basically DCA into crypto. Every time I spend money on with my card, and the change rounds up, and I buy crypto with it. They have a feature on there I really like called Ideal Bumps. It's one of my favorite features because it kind of gives you information about upcoming cryptos. Things are kind of hot right now, and I always use that to kind of align what I want to use for my DCAN. And it has been a super helpful trip for me to just use this system to really get the bottoms, the no-thins, the ones no one knows about, or ones that are just at a good position for purchase. So I really recommend RoundlyX.com for basically everybody to get DCA'd into crypto as easily as possible. Alright, so let's go ahead and get that intro rolling. Aw, that is so awesome. Thank you again, RoundlyX.com, for helping us not only get this intro, but help us get this show going each and every other week, as well as the Bitcoin Live network itself. Alright, so I am like literally just trying to get that camera connected right now for you guys, because it is crazy. Alright, today's episode is definitely going to be a fun one. It's one I've been looking forward to for a while. Once I get this camera connected, I can get back to the actual show thing. I got a locked screen. Okay, we might not have the avatar running in motion capture. It's just gone down. We're just going to keep going. We're going to keep rolling with it and let it go on. So, yeah, today, entropy, entropy, and enthalpy. A lot of people really, especially in cryptocurrency, we really fight about this. We argue about it. We discuss it all the time. It's something that people just, they can't seem to really agree on it. And what makes matters worse is we use this for everything. We can't measure anything without it. It is our unit system for measurement, which is what I find to be the most crazy about this whole thing, is we can't agree on what it is, but we use it for everything. And that is just... Oh, hello. I saw my body move. But that's just crazy. Why can't we agree on the thing that we use to ensure we can measure things? So I don't want to just tell you guys these things without giving you some kind of proofs. That's what we're here for today, right? Change your mind with proofs. So first thing we're talking about is literally the what psychologists or psychists, blah, blah, blah. The physicists. Yeah, sorry, I was on the psychics for a minute. American Journal of Physics. They actually have multiple articles, multiple different papers and studies just on why people cannot agree on the meaning of entropy. And this article right here, if you have access to it, it's probably one of the best. Let's go ahead and get you that QR. I really think this one breaks it down, and just in the abstract, of what we're really going to be looking at. Discussions of the foundations of statistical mechanics and how they lead to thermodynamics and the appropriate definition of entropy. And the reason why we're using thermodynamics with entropy is that's where we can actually see entropy happen. So it is where entropy actually technically comes from. The ideal of entropy comes from. I believe that this guy believes that some or all of their disagreements about what the meaning of entropy is differ from unstated assumptions, which basically cause all the problems. And unstated assumptions is the whole entropy reasoning, right? It was originally inserted into maths to make maths work, that were known to work. We could physically see them work, so entropy was added to mathematically allow them to work. And we will actually give you a chance to see that proof a bit later. Now, here is a really good pre-search if you want to come in here of just this topic alone. If you just want to do more information research on it, here's the actual paper I went to. There's a bunch of them here, and a bunch of different websites that just explain why people can't agree on it. Because it is such a hot topic, and I believe I have the considerative reasoning, which is everybody looks at entropy in one way when it's all possible ways, which is the confusing part, and we'll get into that. So before we get into a whole lot of very complex information and stuff, I'm going to use basically this really fun website, Wolfram Alpha, to actually help us explain all the different parts of entropy, because it is quite confusing. And I say it like that because, well, people can't agree on it, so it must be confusing. So entropy, as in a physical quantity, is an absolute. It has a symbol as an S. We can actually see its basic dimensions, so we can measure it. We know it's joules per Kelvin. It's scalar, so it's going to be in a single array. It's going to go in one direction. And we see it has subcases. These subcases kind of break down that there is more entropy than entropy itself. There is entropy change, negentropy, there's relative entropy, skew entropy, and that's the basic few. So each one of these is going to pretty much tell us more information about entropy. And, well, I mean, let's just start at the basic other form, skew entropy. So skew entropy is a physical quantity. It has the same dimension and standard and type as entropy, and it is absolute entropy. This is what most physicists would call entropy, and even physical constants. So this could even go to most engineers would probably say this is what we would really call entropy. It is the actual skew from one to another of change. And this is the way to measure it. This is the very minimal base way to do it. So now, what's the opposite of this? Oh, you know what I just realized? I'm not giving you the QR. So the first QR for entropy, Wolfram Alpha. Second QR for skew entropy, Wolfram Alpha. And the one we're about to do right now, which is negentropy. And there is actually more than one form of this. This is negative entropy is the most common way to say it, but I've even heard like exotropy and things like that. But this negentropy or negentropy is the most common or the way to do it, and it is technically a physical quantity. It is, as you can see, it is a shifted joule. It has the exact same dimension. It is still the same type of unit. It is joule over per Kelvin. It's still scalar, so it's still in one direction. It doesn't go backwards. It's like an array. But we can see negative entropy, syntropy, and it is also an absolute entropy, which means it is a base. It is the offset of the skew entropy. And I like a good way to I like to describe this. This is like entropy friction. Negentropy is the friction of inside entropy. When things move in entropy, there is some kind of friction. We're going to call this negentropy. Okay, so if we look at this image, this one right here, this is the thermodynamic perspective of entropy, and this is how we can actually physically see entropy. In this case, this is entropy leaving. This is the most common way to see it. Let's get you a QR real fast. And basically, we're just taking something that's hot, in this case, water, or air, or something like that, and we're making it cold. Heat, steam, whatever, we're turning it to water, then ice. To do so, we see that there's something that has to be removed from the equation. We can see we have Q and S, and then we have a W, and then now it's still Q and S, but there's a W missing, and W is part of Q. So we can see something physically leaves, we can see where it's at and why. And if we just do this the opposite, we go from cold to hot, we would insert W into that exact same spot. So we know the exact thing that causes it physically. We can find it, we can point it out, we can show you. Like, there's a million ways. This is soothful. You can see it on your own without anyone else telling you what's going on. When you turn on the fire, you can see the steam eventually come out. When you take the hot water and throw it in the freezer, you will eventually, especially if it's there, you'll be able to see it freeze. So, it's possible. So now let's go to relative entropy. Because relative entropy, as you can guess, is relative to something. It is still, in this case, a physical quantity. Because there's more than one way to assume relativeness. In case you're wondering, relative is not an exact. It's fun. So, if negentropy is a negative force and entropy like a friction, then relative entropy will be the change in information of the entropy. Another way you can describe it is it's the heat caused from the friction. So that heat could be considered some type of informational value, layer, or basement. And we see relative information entropy is a physical quantity, d to the Kelvin line. So as a physical symbol, it's now being represented in kelvins instead of joules, like the other ones. And so this is just the other side of entropy. It is information based. A lot of times it's going to be binary sets or things like that, or it's going to be a value, voltage, something like that. Normally common seen in bit standard, and it's scalar, so it's still one direction, like a blah 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 forward line array, an array, yeah. So we can see it's also information divergence, information gain, or Kullback-Leibler divergence, which is just information entropy. As we see, it's base formation. So this is just the divergence from whatever it was to what it is now. It's the change. It's the physical difference of in that information. Well, I can't just show you one relative thing and not cover the other relative thing. So here's relative entropy, referring to the mathematical definition, because we actually care about, really, the mathematical formations of entropy. Bro, why is my dang avatar looking at the wall? Whoa. Why is all my things gone? Okay. You guys see that? I don't get it. It's not working with me. Well, let's go back to mathematical entropy. So mathematical entropy is the Kullback-Leibler distance. So the mathematical form of relative entropy is the physical distance that's been changed or moved from one entropy to another. And the distance is relative, meaning it doesn't really matter. It's just meaning that it's not in the same as, it's not the same as before. So if we look, we can see right here, it won't let me highlight, I can zoom in though, right above me. P to Q is not equal to P to Q upon the forms of D. And if we look, we see that big echelon to the k to the p to k to the log of 2 inside the brackets p to k to q to k. So what that really does is that it is the average mean of the in total depth of the average of the two objects on average. So the average of these two objects averagely with one on top of the other cannot equal the same thing with but flipped, where q is over p instead of p over q. So either it's a negative or it's 0 when you ask if p is equal to q. And that's kind of a point to what we're looking at. Because it's a distance, it can't be the same distance. And when you see, it is a mathematical information. It is just some, ways to look at it, but basically it's a theory of information. Because it's relative, it's kind of hard to prove. But proof is in the beholden. That's what makes it hard. It's not actually hard to do, it's just not everyone will believe what they see. Okay, but if you look at this equation, and most people looking at it will probably think, bro, I need like 2 degrees to explain that. But there's other ways to explain that without it. So, first off, this is entropy. It doesn't really look like entropy. It is. This is actually entropy. If you're looking at galaxies, when we look at entropy, it's like a surface tension across the whole thing. So if we look at the coloring of these galaxies, we can see their amounts of coloring shows the amount of surface tension. The darker the coloring, the higher the surface tension. The less the coloring, the less the surface tension. And then we can also see the major amounts of mass by the amount of brightness from each thing. We can see the amount of activity from the brightness of each thing, the amount of mass from the physical size of the dot placed. And so, like for example, the one right behind me, which I'm going to now move up to the side, right over there, it should be right over there. For some reason my thing is on backwards. Probably from when it reset my calibration. So that thing right beside me to my leftish has a really scattered entropy. While like the one right on the other side of me, it's really selective. The one now to the other side of me is kind of selective, but very not selective. So this is entropy, in relative entropy at that. So what about the actual change? Actually, you guys might want to see this picture. I keep forgetting to show you guys these QRs. Make sure you guys get all these QRs. So, when we want to say actual change, though, we're talking about entropy change. An entropy change is a physical quantity. It is the average of S, which we saw earlier, which is entropy. And we can see it's measured the exact same, joules per Kelvin, scalar, so it's an array, and it is absolute, so it's the base. So even the average of entropy is entropy at its core. The reason that is because everything with entropy, it always wobbles to the median. That's kind of what entropy does. If it tries to keep its surface tension intact, and to do so, it has to wobble everything to the median. Here we are actually looking at something being rotated 90 degrees, and that triangle being rotated 90 degrees, we're watching one of the tips. One of the tips is kind of moving around. It's not staying in one spot, right? So, because that tip is not staying in one spot, it's moving around. What that does is it gives us this. Everything ends up being to this mean thing. Everything ends up at this one position. You see it 3 different times in that same spot. And even though the height is the same, relatively, from 0 to 90 degrees, it still has this change that wobbles to the median. So if we look at the actual mathematical determinations and real definitions, I guess you could say, of entropy, you're going to see it's exactly the same stuff. Nothing's changed. Here's that one formula we saw earlier. Joules per Kelvin, everything's exactly the same. Only thing this really does is shows us we can actually see there's tons of ways entropy is viewed by different people. So it's kind of like every time entropy has a use case, they look at it differently. And looking at information entropy, you can see it really kind of helps show you that it's about the averaging to the mean. I mean, everything's kind of averaging out to y, right? Hit more thermodynamics. If we go like this and go entropy, we can see it's got quite a bit to do with thermodynamics. And we see in the paper on the moving force of heat, published in 1850, the second law of thermodynamics introduced the concept of entropy because it could be seen. 1870, they introduced the viral theorem, which applies to heat, which kind of helps prove the ideal of entropy. So let's look at viral theorem. Viral theorem is this ideal that no matter how do you want to use entropy, there's a form, a way to use it. It's a singularized statement that can be done in more than one way. So here is a basic formula, and as we go down, we can see depending on the case use, depends on the actual use or type of formula used or how it's going to look. Even though it's the exact same formula, it's just because use case, it does have some changing. With some visual differences, like here in quantum mechanics, I actually get a whole new section. And there's one part where we just duplicate the first section. So, dark matter, data analysis, generalizations, relative information, entropy, statistic, that all sorts of things. Entropy can be used to explain just basically anything. Viral theorem helps explain that information. So in the book Entropy and Life, which if you actually read on the whole Wikipedia thing about entropy, this was mentioned tons of times. Researching whoa, go back, son. Research concerning the relationship between the thermodynamics quantity, entropy, and both the origin and evolution of life began around the turn of the 20th century. So basically, both of these ideals came around the same time frame, right? So in 1910, this guy, Henry Adams, distributed this thing, a letter to the American teachers of history, proposing the theory based on second law of thermodynamics and the principle of entropy. Basically, we should change how we look at history based on entropy. And if we go down here, it's the same formula, it's just a lot more cleaner to look at. And it works. It's the most basic form of entropy consideration. We have negative entropy, but then we have this thing, Gibbs free energy. And for me, this means a lot. So like in recent years of thermodynamic interpretation or evolution, the relation to entropy has begun to utilize the concept of Gibbs free energy. Rather than entropy, this is because of biological processes on Earth kind of take place in a roughly constant temperature and pressure, a situation in which Gibbs free energy is especially useful to express second law of thermodynamics. Basically, Gibbs free energy really explains how we use quantum machines and stuff like that. We have to get them down to a very base zero of super cold so that we don't want to lose any energy when using the machine, so that way there's no energy loss, no heat gain, and we can do stuff way faster than normally. And we can see the formula is still exactly the same. It's averaging everything, but it's just the total average of Gibbs free energy is the total average of everything, the entropy, which is everything plus its sum, minus the average of the, well, not the average, but the absolute temperature of the system multiplied by the average of the entropy, or the surroundings of the system. So even in the system, entropy is involved. Even in the system, entropy is involved. So entropy is inside entropy, even when entropy is its own entropy. Not enthalpy. Enthalpy is the last thing, right? We haven't really gone in here. We haven't really explained entropy yet, but we will. We will. So entropy is the sum of thermodynamic system, internal energy, and the product of its pressure and volume. So basically, it's the sum of its internal workings and the sum of its outputs. That's really what it is. And even in this case, we still have entropy in the mathematical formulations of entropy. So even in entropy, there's still entropy. So most entropy is considered, like this, basically U multiplied by S by V, space times volume. or entropy by volume. But also entropy is also considered in here, which we still have S, which could be space, but in this case it's entropy. This one over here, we still have entropy. In some of these cases, we have multiple forms of entropy. So, entropy is always entropy when entropy is entropy. The reason why it's so confusing is because everyone forgets that there's more than one type of space. And when we say that, we mean there's more than one consideration of space at all times upon us. We're in the third dimension. We have 3 dimensions of space forms in our presence. Now I say there's 4 forms of space in our presence because you can't see a form of space on that line of space. There's another way to prove that, but that might be for a future video. But let's just get a little bit more into these 3-dimensional consideration thing. Because whether it's an elliptic, Euclidean, or hyperbolic depends on what we're going to be looking at. So here we can see elliptical, it's mapping a triangle on a curved surface. Euclidean is mapping a triangle on a flat surface. Hyperbolic is mapping a triangle on basically the opposite of an elliptical surface. So this is the same triangle on all 3 surfaces. They all map out to 180 degrees, which is an average common in entropy. So if we look right here, we can see there's something called Euclidean and non-Euclidean. So Euclidean is just a flat space. Non-Euclidean is everything else. Cool. You can see the same 3 lines on all 3 objects to see how they differ in interactions with their space. Then we have different geometry types for all 3 of these. So here's starting to see where the problem occurs. Because there is different geometry for all different types of space, trying to determine entropy with just one type of space is the issue. You'd have to actually consider it for all 3 types of space, plus your 4th space, which is the average of all 3. And if we go into something like mapping topology, we can see entropy even more. So A1 shows a standard triangle, what it's supposed to look like, flat Euclidean surface. A2 shows it on a non-Euclidean surface. We can even see the points of degree dissection of difference where the object or the cone goes from being flat to folded. And we can see the representation of what that means in B, where we have a flat sphere now being cut and folded to turn into a cone. Same space, just mapping topology. Now C, we can map it through, if it's Euclidean, it comes out a line spiral. If it's like spherical, C2, it's going to be fastened, and then if it's hyperbolic, C3, it's going to be unfastened. So based on the topology, can also determine the type of space we're in. And if you notice, all 3 of these little triangle things they have areas that overlap and areas that don't. Super important. So this is what they consider the basic law of thermodynamics. You have 3 things talking to each other. There's no loss. There's no gain. But in reality, there is loss from one and a gain in another. And that is why you see the 2 ones going from A to B and the one from A to C, those are solid. Okay, because there's either a loss or a gain there. And then B to C is no difference. It's a divided line. Okay. So, now you can see the unrealistic formation of entropy, which you can see it's not very good to do it like this because it's very unrealistic. But it also shows the problem. Assumptions. So here is a mathematical assumption where it kind of shows entropy, and we can see there's a really big mathematical determination to explain how even with loss, with entropy, we can just add this GT, so to speak, into that loss to resettle it. And so there's a programmable way to handle entropy mathematically. And it just shows that one tiny simple step in math can actually be an extremely long process physically. For example, adding heat to a plate to boil water, which is where a lot of this comes from. GT is the heat. Well, that's not just fire, that's the system running the fire and the way it's all being held together and a bunch of other stuff. But mathematically, it's just this extra little bit of well, technically, I guess it's like the C1 equals 2, but it's the log of f across on the right side. That's really where that little insert is at. But we consider that C1 equals 2. So then we know there's multiple forms of C. There's the first one we're looking at equals 2, which means it's an addition of 1. Yeah. So here we go again. Here is, again, remember this one. We get to see the change. So here is when we go mathematically, what is entropy? Here's a good way to explain it. We have a highly ordered ball. We have a highly disordered ball. Oh, gosh dang, man. Highly ordered ball and a highly disordered ball. Okay? So, because of this, all we did was just change the space in the puzzle. It's a flat puzzle, so we just move the parts further along. And just doing that, it kind of looks scattered, but it's really not. Here we go, another exact same ideal principle, a highly ordered ball and an unhighly ordered ball. Although you'll see the entropy seen in this one looks way different. You can't tell, really, that the one on the right is the same as the one on the left. All we did was spread the parts apart. But you'll notice this is a 3D puzzle, not a 2D puzzle, which means if I could move this ball in this highly disordered ball in 3D space and move it around, I could eventually get to a point where I could tell it is that ball. It won't be the exact same looking ball because lines won't be perfect because it'll be in different position in space than what we're seeing as it highly ordered. But I could still get that basic shape that it's a ball, including with highlight in the right spot. So, what's the difference? It's just a matter of dimensions in the math. So mathematical dimensions is not the same as what people consider physical dimensions. Mathematical dimensions is just, like if you can look up and down, that's one dimension. If you can look left or right, that's another dimension. If you can look at an angle, that's another dimension. So mathematical dimensions is confusing. The fourth dimension of mathematical is normally an average or internal dimension. Fifth dimension is normally the difference of internal and externals. I mean, we have different ways to explain these different things. But we will want to talk about what we're talking about, which is entropy. Mathematically, we're talking about thermodynamics. Let me show you why entropy is randomness. Because okay. We've kind of proven that entropy is itself in every possible way. It exists on all the different mathematical planes possible because it is everywhere, including inside of itself. Let's explain this more, because the part that's inside of it is a random part, while the rest of it's ordered. So, where's this randomness coming from? Here we have a polymer chain. Dang it, sorry, my thing got calibrated backwards. So here's a polymer chain. In this polymer chain, we can see at the very first one closest to me, that structure has two F points that are going towards each other. The endpoints are focusing at each other, they're like attracted. And if we look next to it, it has a protein molecule. We can see that protein molecule has those F points that are attracted, but they also have these yellow ones that are also attracted with other F points. Same concept, both types are attracted. So when you see the protein being folded, you can see all the orange F's and all the black F's are pretty much attracted to each other appropriately. And then they attracted to each other within that shape. Okay? So that attraction of attraction, so it's effect from effect from effect, causes a new effect that we can see. It just makes things look more complicated than they really are. So, I'm going to break this down. Hyperbolic, okay, hydrophilic. These things do not like water. That molecule and this surface do not want water between them. That's what causes the attraction. That is when we're heating up a plate and creating steam, we can see water molecule droplets attract on the steam on the metal plate. And that's what we're looking at right here. So if we look at this snow crystal being frozen, which is the opposite of what we were just talking about, we still have the same thing here, but now we can see a complex structure, the crystalline of the ice, while it's growing inside the vapor. So there's tons of other molecules around it. We can actually look really closely and see tons of these little F attractions with these tiny molecules are not attracted to the complex shape in the same way. So while having a single plate, they're all attracted to it in the same way. Having a complex shape, they're no longer attracted to things in the same way. Everything kind of moves at its own whatever. It's more random because of the complexity within the shape and the things that are the causes from it. So this is why there's always randomness in entropy, and why entropy always has entropy inside Entropy. It is absolutely insane, but it's one of my favorite ways to explain this. And this kind of brings us back to this thing right here. Because of unstated assumptions, people cannot agree on what entropy really is. And we've seen it. Entropy is something different for every form of layer we look at it. Every mathematical form we look at it, it's different, even though they're all the same. And we're actually, like, the surface tension of everything is what's being changed. I want to explain more of how that is. So let's look at the standard entropy change. If we look at standard entropy change, we will see that they're not really considering a whole lot here, but they are always considering averages. And even if we look at this, it says that basically it's just negative entropy because there's one less molecule, well, two less molecules of gas. So it helps us really measure things that we can't physically see. So here's entropy problems. And we're talking like mathematical entropy problems, not actually like problems, but mathematical problems. So you can see there's no single consideration of lack of entropy and abundance of entropy. And that's because of a standardized assumptions. Yes, we disagree because assumptions change based on the point of the wave function collapse, which is kind of a good way to explain entropy. Entropy is a wave function. When we look at it, it collapses and we get to see some number. So it just means that every time, this means that there's a time element in entropy. And that time element isn't like a real time, it's just an element about time. So entropy is so random that every time we look at it, it's never the same twice. Even if the number is the same, it's not the same because entropy is always measuring back to the mean. So it's always going back to its average. Remember what the average is. And so if you're looking at it every time it's changing, it's flicking as fast as possible, and we're getting every second it's changing. Even when it changes, it'll eventually go back to the normal. So we will get more often the same numbers of output than not any other number. So patterns of randomness become a type of entropy as well. So even how the entropy's average is per time it's looked and collapsed will change how entropy is. So watching entropy changes entropy. Not watching entropy changes entropy. Doing both, not doing both, changes entropy. And in the problems and mathematical formulations for explaining entropy, they do not consider these 2 points, without and with, of abundance and with lack of. So, imagine for a second, we were to do something, I don't know, like watch the background radiation noise or something, and we had like 2 to 4 boxes that gave us the output digit of what that number is, right? Oh, this is what it's outputting. We would see not the same number across all 4 pretty much ever. There's a chance of it, but we shouldn't. But if we had another set of these that just showed us the previous one for all 4 of them, we would actually start to see patterns repeat amongst themselves, amongst the 4 or the 2. And what that really is just that because we can look at entropy in like 4 different dimensions, then they're going to give us 4 different numbers, but those 4 different numbers are all going to end up averaging to the mean, so they start seeing basic patterns of a lot of the same thing. And this is actually a test that anyone can do. This is something that I'm not explaining is actually possible. I just realized I went through a bunch of these. I don't think I showed any of the QRs. I got so excited what I was talking about. My bad. Oh yeah, we got this one from earlier. So, I'm going to give you these pictures. Because I feel a little bad. A little bad. Got excited. I don't know when I stopped. Okay, that one I can't even give you. Okay. So, problems of entropy. Yep. Okay. So, even if we look at entropy in multiple different ways, we will see the always average back to the mean. If you look at the very first one, you know, the lines and stuff, we can see A to B to C to D to A to B to C to D to A to B to C to D to A to B to C to D. So when we have something removed, it still ends up one spot, then something's added to end up in another spot, whatever. Even on a 2-state entropy system, we can see that one state is only directional in one way, the other state's directional in 2 ways, causing entropy. Because one will always be able to adjust the other, and then the other is just automatically changed because of it. So no matter how we do this, we can see entropy always averages to the mean. Every single time, it's just what it does. It is a type of surface tension for everything, including itself, sum of itself, and the output sum of itself. And the outputs of itself. So, let's go back to this ideal of monitoring the background radiation noise. Can we do it with reasonable accuracy, though? Perhaps. But something to note, if you want to go down this rabbit hole, please do. But something to note is that how you want to view this background radiation noise, it will differ based on what kind of dimension you analyze or spectrum for. 1, 2, 3, or 4. And 4D mostly just being a record of 3D over time. So 5th dimension would be a record of all of these over time. Or 3 and 2, and then 6 would be all 3 of them. So that's the idea of having up to 8 boxes. 4 to determine the first 4, and another 4 to show you what those previous 4 were. You could go all the way up to 8, show all 8 forms. Then you should start seeing duplications of numbers in a row at the same time, which set off different types of patterns to view. So a lot of people believe that if we can measure the difference in randomness, that's really what entropy is. It's the difference between one randomness to the next randomness, or the difference in randomness at any point in time, which, if we go back to it, it's that one simplified equation again, d to q over t. And again, none of the p's can equal, and again, we can even go further into dimension of what we're talking about to programmatically determine how we use this equation. So this just shows, again, even in when we go to what we're really saying is entropy, when we really think about it, the only thing we care about what entropy is the measure of difference in randomness at any point in time. The measure of randomness at any different time. And the thing that you'll see here is also blah 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 against a vacuum. Blah 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 blah. So that's the real point here is when it comes to measuring randomness, we consider everything in a vacuum. So with entropy, that should be the only assumption, is that everything is measured in a vacuum. And the reason why that's super important is because that's an assumption that not only can we mathematically determine and understand, blah, 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 but it's like we can physically do it too. We can pull a vacuum and physically see it. And so now we can have correlations between our math and our physicals again, which helps us understand and proofs, which is how measuring works, right? So this would also help us with measurements. Okay, so when we're going back to still measuring randomness, we can see here's an entire paper or whatever on how measuring randomness or the uncertainty within what's going to happen next is more entropy than anything else. And here is the base consideration. Here is to find that, and there's more and more and more and more in here you can go through, but I'm not going to go through this entire paper. The basis of this entire paper is just that basically there's a lot of stuff overlooked in considerations, and because of that, the only thing we actually care about is the amount of uncertainty for the next. And he doesn't map. This person explains it mathematically, so please come read this. It is good. It's a good paper. I think it took me like a few hours to read it. Well, most people probably about an hour or two. So now at this point, you're probably thinking, so what? Now, in this paper, it does kind of explain more of like measuring randomness in a vacuum and how that math works and why it's important. So you're probably still thinking though, so what? Did I change your perspective on what entropy is? I mean, I really don't believe I did. I know normally that's my goal, but entropy, to understand it, it takes time. It takes time. And that's the whole point between entropy, right? You can't just look at it once and get an ideal of it. But one of the things that entropy does is it allows us to measure anything and everything. It is also used against us. It's also why NASA can say things like 2023 is the hottest recorded summer on record, but only compared to the entropy between 1951 and 1980 of the surface temperature. So it only goes up to 1980, and it only starts at 1951, which is a really clear indication of some abuse of information. We can see in here that it goes up in value. Because of this, it causes El Nino, which destroys everybody, which causes disasters, and it's really expensive. And keep in mind, this is official climate.nasa.gov. This is official climate.nasa.gov. And then if we go over here, here's the reason why they don't want to show anything after 1980. You can see after 1980, temperatures just kind of keep going up. We started the age of summer right after we ended an age of winter. That's why it doesn't go to only to 1951. 1951 is the first year where we had a cold spill after a heat wave after the age of winter, after the last ice age. People think that an ice age it freezes everything, but there's ages of winter and ages of summer where there's like 20, 30 years of just like more perpetually either hot or cold temperatures. We can actually prove it. Let's look at this. If we was to see more temperatures going this way, it'd get colder and colder and colder. And we kind of know this because people have been measuring the surface temperature for a long time. And surface temperature is kind of important because most of the surface on this planet is water. So they're actually just measuring the temperature of water at different depths. Well, studies have been saying that started over 135 years ago in 2012. So I don't know if you know how many 135 years before 2012 is, but I have a little calculator to help us out. So let me just find out for you, huh? So in 2012, minus 135, we're looking at 1877. And if we go back, this graph started actually in 1887. It says it started in 1880, but actually 1880 is like right here. So, this graph is showing since this started, which, if we go back, in 1872 to 1876, the HMS Challenger sailed the world's oceans along a specific mile track crossing the Atlantic, Indian, and Pacific Oceans. During the voyage, scientists among 200-person crew took 300 ocean temperature profiles, severing different depths in each spot. Romex and his colleagues compared Challenger temperatures data from modern-day algal projects, which they basically did the very similar thing, as well as they've measured other things every 10 days for a period of time. And that, from the two data sets, they were able to determine that the increase in the ocean surface temperature actually started 135 years ago, which they can guarantee started at least 100. Okay, the average temperature of the ocean water 135 years ago was a certain degree difference, a 1.1 degree difference, right? That degree difference actually started changing 100 years ago, like before that. So more than 100 years ago. It's confusing. They're saying this 1.1 degree change in ocean temperature started over 135 years ago and potentially 100 years before that. And really what they're saying, what you should be getting from this isn't a whole lot of mumbo jumbo. What it should be is that in 1872 to 1876, they were already studying the ocean's temperature. And then in 2012, the only difference in degree was less than 2 degrees. And they were able to prove that, like, most of that happened over 100 years ago. Before they ever started measuring. 100 years before 1872. So here on NASA.gov, make sure you get this one. But NASA.gov again, we can actually see like kind of like live videos of temperatures, chlorophyll, water vapor, and these are actually really important because if you look at these different things, you can see that whenever you have an area of hot water, there was just an area of active chlorophyll, just because there was an area of coldness, just because there was also during a time of area of high water vapor, because high water vapor over an area causes cold water, which then allows things to grow, which causes heat in the water, and the water vapor had already been moved by then, which then creates more water vapor, and well, some of the things are dying as the water's getting too hot, causing the water vapor, which then cools down the water, which then allows things to grow, so it's a cycle. And the sea surface temperatures have a large influence on the climate and weather. For example, every 3 to 7 years, a wide swath of Pacific Ocean along the equator warms 2 to 3 degrees Celsius. And if we look at that, we also see that responds to a chlorophyll attraction that happens around that time frame, that right before that does happen. This also is why we have the hallmark patterns called El Nino and changes in rainfall pattern around the globe, causing heavy rainfall in the U.S. and severe droughts and like in Australia, Indonesia, and southern Asia, so the southern hemisphere. On a smaller scale, the ocean temperature of these also creates stronger like hurricanes and things. And if you go through and you read more about this stuff, and you go through and you look at different maps, and the reason why they're measuring the water temperature is it's the most surface to measure. The other reason why they do it, they say it doesn't change as often, which we can then, they also can prove that it changes on cycles, in cycles, for reasons. And yeah, it's basically they are disproving their own information. When you take the entropy out of the measurements and you look at it over time in the fourth dimension, it's easier to see why things are happening the way they are happening. It isn't accidental. You see the polars get bigger and smaller. We see the chlorophyll grows and distance, and we see the water vapor increases and moves, and it all creates this entropy effect on the Earth. The Earth has its own entropy. And really, when we go down to why this matters, why all this matters, this part's going to blow your mind. Probability is not the same as randomness. Oh, I'm backwards again. So probability and randomness are completely different. Randomness is we don't know. It's the possibility that we can determine what's next or can't determine what's next. Probability is the state of likelihood, meaning randomness is more real. I can prove I can prove randomness. I can prove why that randomness happened. Okay? I can prove all these different things about randomness. But probability is just an assumption of belief. When we look at these graphs that prove climate change, that prove all these different things, they're probability graphs based off of data. They're giving you probabilities based off of data. But when we look at the data, the entropy falls, and we can see it clearly. But the thing is, we don't get real, true data because it's only compared to other things. Because we have to have entropy to measure. And because we can't agree on entropy, how can we agree on the data that we receive? Well, this is actually why no one really agrees on a lot of major things nowadays. This is why a lot of people don't agree on, the climate change and the non-climate change. Or does carbon emissions actually make a difference? Do humans make a difference? Do animals make a difference? Do all these things matter? Does the food you eat consider to the amount of times you fart make a difference? I mean, it comes down to more people like probability information, less people like randomness information. Probability looks pretty and can scare people easier, while randomness is just more confusing and less information of it, but it's more provable. Randomness is provable. Probability can never be proven. It can only be wait to see if it happens. And I hope that is what blows your mind today. Because believe it or not, that's the perspective I was hoping to change. Alright guys, I'm sorry. My thingy not working again. Yeah, I can't even play the outro. I'm sorry about that, everybody. I had a really cool outro, but it's not playing today. I'll have to try it again next time. Thank you everybody for showing up. Hope you guys enjoyed it today. And